Right, so still talking about first order equations, but now we're going to take a small break from solving these ODEs and think about visualizing these ODEs, specifically visualizing their solutions. So this is about autonomous ODEs. The reason why we're studying autonomous ODEs is just because their solution diagrams are pretty predictable. So first of all, what is an autonomous ODE? I'm going to define that. So definition. A first order ODE is called autonomous provided that there exists a function, call it f, such that the ODE can be written as y prime equals, so in general, for a first order ODE, y prime is always a function of x and y. So usually we would say this is a function of both x and y. For an autonomous ODE, it's just going to be a function of y. So no dependence on x. Okay. Remember, in our first lecture, we talked about the ODEs that have y prime equals f of x, and those are just integrals. But now we're saying it's only dependent on y. So as far as solving these goes, you can always do it by separation of variables as long as you can integrate 1 over f of y. But we're not really interested in solving them so much as diagramming their solutions, at least for today. So when you have an autonomous ODE, there are some solution curves that are going to be more important than others. Those are called equilibrium solutions. So, definition. Let dy dx equals f of y be an autonomous ODE. An equilibrium solution of the ODE is a solution of the form y equals k, where k is a constant. So k is a constant, and f of k equals 0. Okay? In other words, these are just all the solutions that are constant solutions where this f of y is 0. So dy dx is 0. So these are very important for drawing the diagram of solutions. So we're just going to take one example. Y prime equals, let me say that this is an example. So what we want to do here is diagram all solutions of y prime equals y squared minus 6y plus 5. Okay. So for autonomous ODEs, when we say diagram all the solutions, first of all, we're only concerned with positive values for the independent variable, which I'm going to call t in most cases rather than x. Why? Because most of these ODEs have applications to physics where the independent variable is time. Oh, and I just realized this should be dy dt. Yeah, sorry about that. So the first part of drawing the solution curves of this is to find the equilibrium solutions. So equilibrium solutions would be where this right-hand side, and therefore the left-hand side as well, is 0. So this right here can be factored as y minus 5, y minus 1. And then if we think about where that is 0, well, there are two locations where that is 0. One of them is y equals 5. The other one is y equals 1. So let's indicate those on our graph. Here's the t-axis. 1 we'll say is like right here, then 2 will be here, 3, 4, and 5. So we have y equals 5 and y equals 1 as two solutions, equilibrium solutions, therefore constant solutions, therefore just horizontal lines. Okay, so the next thing we need to do is construct what's called the phase diagram. So let dy dt equals f of y be an autonomous ODE. The phase diagram of the ODE is a number line that illustrates the sign of y prime on each side of the equilibrium solutions. Okay. Now this number line is usually interpreted as being along the y-axis, because what we're doing here is we're taking 5 and 1, and we're thinking about, okay, below 1, what is the sign of y prime? Between 1 and 5, what is the sign of y prime? And above 5, what is the sign of y prime? So, if you look at a value less than 1, like 0, let's see here. This would turn into 0 minus 5 times 0 minus 1. That's a positive number. So we're just going to put an arrow facing up here to indicate that y prime is positive. If you take something between 1 and 5, such as 2, then we have 2 minus 5, which is negative, times 2 minus 1, which is positive. So that's going to be negative. And so in this region, we put an arrow facing downward. And then finally, if you select something larger than 5, like 10, then you get something positive times something positive. So this is going to be an arrow going upward. And then that y-axis is what we call the phase diagram. Now, as you can see, for y equals 1, the arrows are pointing towards it, whereas for y equals 5, the arrows are pointing away from it. We have names for those. So let y of t equals k be an equilibrium solution. We say that y of t equals k is stable, provided that the arrows of the phase diagram point toward the solution. Otherwise, we call it unstable. Okay. So we have one stable equilibrium solution because the arrows are pointing towards 1. So this one is stable. So stable. And then on the other hand, we have an unstable equilibrium solution because these arrows are pointing away from 5. So 5 is unstable. Now, it is possible to have an equilibrium solution where on one side the arrow points towards it and on the other side it points away. Some people call that a semi-stable solution, but I'm not going to require you to go into that much detail. Unstable and stable is fine. Okay, so at this point, we are pretty much ready to draw all of the solution curves. There's just one more thing that we need to be concerned about. So, the phase diagram indicates that in... one thing I forgot. By Picard's theorem, none of the solution curves will cross. What that means is that these equilibrium solutions have partitioned the plane into sections. Okay? You can't have a solution curve going from one section to the other. No, that violates Picard's theorem. So what that means is that all the solution curves are in these patches of the plane divided by the equilibrium solutions. So the only question left is, what is their concavity? So for an unstable equilibrium solution, the solution curves are just going to blow away from the equilibrium solution. And so we're going to get a behavior that's kind of like this. And it's also concave up. For this one, the solution curves need to be attracted to the equilibrium solution because it's stable. So we'll get behavior that kind of looks like this. And this is about as much detail as I need you to go into. Just draw a few solution curves in each patch. The only question is, what happens in this region? Okay, that is a little more complicated because, okay, we know that the solution curves blow away from 5 and move towards 1. That's great and all, but do they do it like that? Or do they do it like that? Or do they do it like that? Well, all of these can be distinguished by just looking at the concavity of the curve. So to look at the concavity of the curves, we just need to do it the same way we did in calculus 1. You take the second derivative and figure out where it's positive and negative. So we'll take the second derivative of y. That's going to be y prime prime. Now note that we are taking the derivative with respect to t, not y. Okay? So the answer here is not 2y minus 6. That would be the derivative with respect to y. What we want is the derivative with respect to t, so we actually have to use the chain rule here. 2y y prime minus 6y prime. Okay. This is 2 y minus 3 y prime. And then y prime, we already know, is y minus 5, y minus 1. So this gives us y equals 3. What is the significance of y equals 3? Well, it's a inflection point of the graph. In other words, it changes concavity at y equals 3. This line is called a sigmoid. So let me draw it here. At 3, we have this line at which all the solution curves change their concavity. So at first they're going to be concave down, blowing away from 5, but then when they cross this sigmoid, they're going to turn concave up, going towards 1. And other solutions will behave the same way. And what if a solution... So by the way, just want to point out here, the different solution curves all correspond to different initial conditions. The initial condition is the location on the y-axis where these things begin. Y of 0. So what happens when we take an initial condition that's less than 3? Oh, no problem. That just has to be concave up for all values of t. All positive values of t, I should say. Okay. And so the solution curves look kind of like this. Now, You don't have to draw this many solution curves. I'm just doing it to illustrate how this works. Okay. The reason I say that is because these solution curves must not cross. And the way that I've drawn it here, it's getting pretty cramped. But they don't cross, okay? No matter what, they do not cross because of Picard's theorem. So let's do another example. Okay, same directions. We're going to sketch all the solution curves of the autonomous ODE. Y prime equals y squared minus y. So, first thing we have to do is find the equilibrium solutions. That means setting the right-hand side to 0. So let's see here. We have y squared minus y equals 0. That's the same as saying y times y minus 1 is equal to 0. And then that gives us two solutions. One of them is y equals 0. The other one is y equals 1. So we already have some very important information that we can put on our graph. And again, we're only going to consider positive values of t. So y is a function of t. Okay, 0 is an equilibrium solution, so let's mark that, I guess. And then 1 is an equilibrium solution, so let's mark that as well. And there are our two equilibrium solutions. All right, next up we need to construct the phase diagram, which is to label the y-axis with the appropriate arrows to indicate the sign of y prime. So let's see here. If you take a value of y that is less than 0, then let's see here, what would dy dt be? Well, dy dt, as we know, is y times y minus 1. So if you take a value less than 0, is this positive or negative? Well, you take one, like negative 1. We have negative 1 times negative 2, that's positive. Okay? So we have an arrow pointing up in the region below 0. Next, if you take something between 0 and 1, like 1/2, is this going to be positive or negative? Well, let's see here. 1/2 times negative 1/2, so that's going to be negative. So in the region between 0 and 1, we have a negative derivative, and therefore the solution curves will be moving downward. And then finally, if you have something larger than 1, like 2, you have 2 times 1, which is positive. And so in this region, we have a positive first derivative. Okay, so that already tells us, first of all, that the solution curves above 1 are going to be concave up and increasing. So we're going to get behavior that's kind of like this. Next, we're going to have increasing solution curves below 0, but of course they can't intersect with 0 because of Picard's theorem, so therefore they have to be concave down. The only question is what happens between 0 and 1. So again, we take the second derivative. Well, let's see, that's going to be 2y, y prime, minus y prime. This is 2y minus 1 times y prime. Y prime we already know is y times y minus 1, so this is 2y minus 1 times y minus 1. So, y equals 0 and y equals 1, those are already equilibrium solutions. But the sigmoid is when 2y minus 1 equals 0, or in other words, y equals 1/2. When y equals 1/2, we have a change in concavity. So we will just draw that sigmoid. So now let's see. The solution curves need to go down, so they need to blow away from 1 and move towards 0. So that is exactly what they'll do. And just like that, you have a diagram of all the solutions of your autonomous ODE. Okay? Let's do another one. Oh, by the way, I forgot to mention whether the equilibrium solutions were stable or unstable. So this one, the solution curves are coming towards it, and the phase diagram is pointing towards it. So this one is going to be stable. As for the other one, the solution curves are blowing away from it, so this one is unstable. Okay. Now then, let's take a look at the autonomous ODE y prime equals y minus 1 squared. Okay, so for this one, there's only one equilibrium solution, and that's when y equals 1. Y equals 1 is the only value of y that would give us the right-hand side being 0. So, the t-axis and the y-axis, and let's mark y equals 1 right here. So that's an equilibrium solution. All right, next up we need the phase diagram. So, take values of y that are less than 1, like 0. If you have 0, then you have 0 minus 1 squared, that's positive. So we have arrows going up in this region. And then if you take something larger than 1, like 2, 2 minus 1 squared, that's also positive. So we have arrows going up in this region as well. So this is what some call semi-stable, because one arrow points towards the solution, but the other one does not. And for this one, that's about all you need to do, because there's no way you could have a sigmoid. There's no way the inflection could change, or the concavity, I mean. There's no way the concavity could change. All the solution curves are just going to go up in this region and approach 1. And they're going to go up in this region and move away from 1. So all the solutions look like that. Okay. So let's just talk about an application of how this could be used in, well, applied math or biology. Let's suppose that you have y denoting the population of a certain species at time t. So suppose that it satisfies an ODE that looks like y prime equals negative y cubed plus 6y squared minus 8y. So the question is, what is the minimum viable population and what is the maximum sustainable population? So what this is asking, minimum viable population means a number of individuals of your species such that if you go beneath that number, extinction is guaranteed. By maximum sustainable population, we mean the most individuals you could have in your population without running out of resources eventually. So, we can handle this the way we would handle any other autonomous ODE. We say 0 is negative y cubed plus 6y squared minus 8y in order to find the equilibrium solutions. So now you can factor out a negative y and get 0 equals negative y times y squared minus 6y plus 8. That can be factored further, right? That can be turned into 0 equals negative y times y minus 2, y minus 4. All right. So that gives us 3 equilibrium solutions. Y equals 0, y equals 2, and y equals 4. So let's draw them. So here is our t-axis, and here's our y-axis. Let's say 1 is here, 2 is here, 3 and 4. And of course 0. I can do better than that. It's a little bit better. So now the next thing we need is the phase diagram. So let's see here. Y prime, we know, we can factor into negative y times y minus 2 times y minus 4. So, if you pick something less than 0, well, first of all, let's recognize that less than 0 members of a population does not make sense. But just to do the math, if you pick something less than 0, like negative 1, this becomes 1 times negative 3 times negative 4, which is positive. So beneath 0, we have solution curves moving upward. Between 0 and 2, such as 1, we'd have negative 1 times negative 1 times negative 3, which gives us a negative value. So we have solution curves moving down in this region. Then if you take something like 3, we have negative 3 times 1 times negative 1, and that's positive. And then finally, if you take something greater than 4, like 5, you'll have negative 5 times 3 times 1, which is negative. So, what's going on here is solution curves are going to fall down like this if they start above 4. What that means is that having a population up here is not sustainable. It's eventually going to die out at a faster rate than the birth rate until you get to 4. Then, between 2 and 4, we're going to have some kind of behavior that looks kind of like this. And yes, we can be more detailed about this. There is a sigmoid and so on. But that is the idea. So if we have a population between 2 and 4, it's eventually going to increase to 4, giving us 4 as a stable population. And then finally, if it's less than 2, then you're going to get this kind of a thing happening, which leads to extinction. So 2 is an unstable population. And 0 is a stable population too, but hopefully that was already obvious that if you have 0 individuals in your population, then you will continue to have 0 individuals in your population. And if you have 1 individual in your population, eventually you'll have 0, provided it's a sexually reproducing species. In any case, what we get here is that the minimum viable population of this species, we're going to get extinction if we are less than 2, so the minimum viable population is 2 units. The maximum sustainable population, well, that would be like the limit as t approaches infinity. In our case, that would be 4, because if you take a different maximum, well, that's eventually going to decrease down to 4. Okay? And so that is the idea behind sketching solution curves of autonomous ODEs. That's all for today. See you in the next one.